The universe has a weapon. It's not a metaphor. It's not science fiction. It's physics. Right now, as you watch this video, you are alive, breathing, existing. But somewhere in the cosmos, a star is dying. And when it does, it will release more energy in a single second than our sun will produce in its entire 10 billion year lifespan. This is a gamma-ray burst. Astronomers call them GRBs. They are the most powerful explosions in the universe since the Big Bang itself, and they are absolutely terrifying. But here's what most people get wrong. A GRB is not an explosion like a bomb. It's not a firework. It's not a supernova. When a hypergiant star runs out of fuel, its core collapses. The outer layers fall inward at a quarter of the speed of light, and what happens next defies everything we think we know about physics. The question isn't whether these exist. They do. We detect them every day. The question is, has one ever been aimed at us? Gamma rays are the most energetic form of light in the universe. Their wavelengths are shorter than the nucleus of an atom. They carry so much energy that they can pass through dense matter like it's nothing. They are completely invisible to the human eye. If a GRB went off right next to you, you wouldn't see it. You would simply cease to exist, and you wouldn't even know why. There are two types of GRBs: long bursts, lasting more than 2 seconds, and short bursts lasting less than 2 seconds. Both are cataclysmic. Both create black holes. Both could kill a planet. Long GRBs occur when a hypergiant star, a star over 30 times the mass of our sun, collapses into a black hole. It's the death scream of a cosmic giant. Short GRBs occur when two neutron stars or black holes collide. They spiral inward for millions of years, emitting gravitational waves. Then, in the final milliseconds, they merge, and the explosion is so violent it creates the heavy elements. Every atom of gold in your wedding ring, every atom of platinum in your catalytic converter, every atom of uranium in a nuclear reactor. All of it was created in a neutron star merger, in a kilonova, in a GRB. You are not just made of stardust, you are also made of gamma-ray burst debris. The elements heavier than iron in your body were forged in the most violent explosions in the universe. Let's talk about scale. A single GRB releases about 10⁴ joules of energy in 1 second. That's a 1 with 44 zeros after it. To put that in perspective, our sun will release about 10⁻43 joules over its entire 10 billion year lifetime. That means a single GRB releases 10 times more energy in 1 second than our sun will produce over its entire life. 10 billion years of sunlight, compressed into a single heartbeat. The common mistake in science fiction is to imagine explosions in space as expanding spheres, like a grenade. A supernova is like that. It explodes outward in all directions. But a GRB is not a grenade. It's a sniper. All that energy isn't released evenly. It's channeled into two narrow beams, one from the North Pole, one from the South. How does this happen? When a hypergiant collapses, its magnetic fields don't disappear. They twist, they coil, they funnel all that catastrophic energy into ultra-narrow cones, less than 2 degrees wide. A supernova is a hand grenade. It spreads its energy in all directions and weakens quickly. A GRB is an armor-piercing bullet. It channels the death of an entire star into a straight line across the cosmos. These beams travel at 99.99% the speed of light. They carry more energy than the sun will emit in its entire life, and they are incredibly narrow. Narrow enough to miss us. Narrow enough to hit us. The further the beam travels, the wider it gets. At 3,000 light-years away, the beam is still narrow enough to be deadly. At 50,000 light-years away, it's spread thin enough for our atmosphere to absorb it harmlessly. So the question is, where is the nearest hypergiant star, And is its rotation axis pointed at us? It's a question of geometry, of cosmic alignment, of mathematical precision. Astronomers have identified several Wolf-Rayet stars within 10,000 light-years of Earth. These are hypergiants in their final stages. Some are spinning rapidly, some are unstable, some are candidates. One of the most famous is WR104. It's 8,000 light-years away. A binary system, two stars orbiting each other. One of them is a hypergiant, and its rotation axis is tilted at about 30 degrees from Earth. At 30 degrees, the beam would miss us, but it would graze our solar system. It would be visible from Earth. A blinding flash in the sky, brighter than any supernova. And we would see it long after it had already passed. But what would actually happen if a GRB hit Earth? This is where the physics gets terrifying, and it's not what you think. You might imagine the planet exploding, like the Death Star, a massive fireball, debris flying into space. That's not how it works. A GRB doesn't explode the rock. It destroys the atmosphere. It's a chemical attack on the very thing that allows life to exist on Earth. When gamma rays hit our upper atmosphere, they slam into nitrogen and oxygen molecules. The energy is so intense that it breaks the chemical bonds. The molecules split apart and recombine into nitrogen oxides. These nitrogen oxides are deadly to ozone. In seconds, the gamma rays trigger a chemical chain reaction that destroys the ozone layer. Completely, entirely, in a matter of minutes. Without the ozone layer, ultraviolet radiation from the sun reaches the surface. Unfiltered, direct, deadly. It's like turning off the world's sunscreen. Phytoplankton, the microscopic plants in the ocean, are the first to die. They are the foundation of the marine food chain. They produce half the oxygen we breathe, and they are extremely vulnerable to UV radiation. Within weeks, the entire ocean food chain collapses. Zooplankton starve, small fish starve, large fish starve, whales starve. The ocean becomes a graveyard. On land, plants lose their ability to photosynthesize. Herbivores starve. Carnivores starve. Within months, a mass extinction event unlike anything since the dinosaurs. But that's not all. The nitrogen oxides create a brown haze in the atmosphere, a global smog that blocks sunlight. The planet cools rapidly. An unnatural winter. A cosmic winter. The extinction would happen in months, not years. Months. The planet would be sterilized at the surface. The only survivors would be deep ocean organisms, and even they would struggle. And for any humans still alive, the UV radiation would cause massive cancer rates, skin cancers, eye damage, immune system collapse. Civilization would not survive. Astrophysicists have mapped the danger zones. If a GRB occurs within 3,000 light-years of Earth, we are doomed. That's the red zone, total catastrophe. Between 3,000 and 10,000 light-years, we enter the yellow zone. Severe ozone damage, massive extinctions. But maybe, just maybe, some life survives. Civilizations collapse. The world changes forever. Beyond 50,000 light-years, the beam has expanded so much that our atmosphere can absorb the energy without damage. We see a bright flash in the gamma-ray telescopes, and we breathe a sigh of relief. Now we get to the mystery. 440 million years ago, something happened on Earth, something catastrophic, and scientists are starting to suspect it might have been a GRB. This was the Ordovician-Silurian extinction event, the second most massive extinction in Earth's history. 85% of all marine species vanished, and nobody knows exactly why. The extinction happened in two phases. First, a sudden ice age. Glaciers covered the continents, sea levels dropped. Then a sudden warming period. The ice melted, the oceans warmed, and the extinction completed. In the early 2000s, astrophysicists from the University of Kansas proposed a radical hypothesis. What if the extinction wasn't caused by Earth's climate? What if it was caused by a gamma-ray burst? The evidence? The extinction pattern. Organisms living near the ocean's surface died first. Those living in deep water survived longer. That matches the pattern of UV radiation exposure, not climate change. A GRB would destroy the ozone layer. UV radiation would penetrate the oceans, killing surface plankton. The deep-sea organisms, shielded by water, would be protected. The extinction pattern matches exactly. There's other evidence. Geochemical signatures in ancient rocks, a sudden spike in nitrogen isotopes, the kind of chemical fingerprint left by a gamma-ray burst. The team calculated that if a GRB occurred 6,000 light-years away, and if its beam was aimed at Earth, the effects on our atmosphere would be exactly what we see in the geological record. So here's the chilling thought. 440 million years ago, a gamma-ray burst may have already hit Earth. It may have caused the second most massive extinction in our planet's history, and we didn't even know it until decades of research. And if it happened once, it can happen again. The universe doesn't care about our civilization, our cities, our achievements. It cares about physics, and physics is indifferent to our existence. Let's talk about the present. Right now, we have satellites orbiting Earth. We have astronauts in space. We have a global civilization dependent on electricity, communications, and infrastructure. If a GRB hit Earth today, the first thing we would notice is nothing. The gamma rays are invisible. They would pass through the planet's atmosphere, triggering the chemical destruction of ozone. Satellites would be blinded, their electronics fried. The astronauts on the International Space Station would be exposed to lethal doses of radiation. They would have minutes to seek shelter. They might not make it. On the surface, the atmosphere would start glowing. The gamma rays interacting with nitrogen molecules would produce an eerie light show. It would be beautiful, and it would be the last thing billions of people ever see. Within hours, the sky would turn brown, the nitrogen oxides creating a global smog. The temperature would drop. The ozone layer would be gone. The UV radiation would begin killing the plants. Civilization would unravel, power grids would fail, communications would break down, food supplies would run out. Within weeks, billions would die, not from the gamma rays, from the aftermath. The cosmic winter would last for years, maybe decades. The nitrogen oxides would linger in the atmosphere, blocking sunlight, cooling the planet. Global temperatures would drop, crops would fail, mass starvation would follow. And through all of this, the survivors would watch the sky, waiting for the UV radiation to fade, waiting for the ozone layer to recover, waiting for a hope that might never come. Right now, NASA's SWIFT satellite detects about 1 GRB per day. Each one is a star dying. Each one releases more energy than our sun will produce in its entire life. Each one is a reminder of how violent the universe truly is. The most distant GRB ever detected was 12.8 billion light-years away. It occurred when the universe was just 600 million years old. We are seeing the death of a star that occurred before Earth even existed. But there are hypergiants within 10,000 light-years of Earth. Wolf-Rayet stars in their final stages. Some are spinning rapidly, some are unstable, some could go supernova at any moment. WR-104 is 8,000 light-years away. Its rotation axis is tilted at about 30 degrees from Earth. That means we are safe. The beam wouldn't hit us directly, but it would graze our solar system. If WR-104 produced a GRB aimed at an angle, we would still see it. It would be a blinding flash in the sky. The satellites would be scrambled. The auroras would dance across the entire planet. And we would know that death had just barely missed us. But here's the terrifying part. WR104 is 8,000 light-years away. That means we are seeing it as it was 8,000 years ago. It could have already collapsed. The GRB could have already occurred. The light could be heading toward us right now. Right now, as you watch this video, a gamma-ray burst could be traveling across the galaxy toward us. It could arrive in 5 years. It could arrive in 50 years. It could arrive in 5,000 years. We wouldn't know until it hit. The gamma rays travel at the speed of light. They are invisible. They are silent. They would arrive without warning. Astronomers monitor the sky constantly. But if a GRB is aimed at us, what could they do? There is no defense. There is no warning. There is no evacuation plan for a planet. We are sitting on a tiny rock, in a quiet neighborhood, in a galaxy that is 100,000 light-years across, and the universe is full of death beams. Let's take a step back. We've talked about stars collapsing, neutron stars colliding, death beams aimed at Earth. It's terrifying, it's humbling, but it's also enlightening. For most of human history, we looked up at the stars and wondered. We saw gods, we saw myths, we saw stories. We didn't know that the stars were dying, that they were creating elements, that they were launching death beams across the universe. Human civilization has existed for only about 10,000 years. The Earth is 4.5 billion years old. That means we've been here for just 0.02% of Earth's history. The universe has been violent for billions of years. Mass extinctions have occurred before. They will occur again. It's not a question of if, it's a question of when. But here we are. We exist, against all odds, and that's what makes life so precious. We are the universe's way of experiencing itself. We are made of stardust. We are made of GRB debris. We are the result of 4.5 billion years of evolution. And right now, we are alive. We have telescopes. We have observatories. We are developing plans to deflect asteroids, to survive on Mars, to build a multi-planetary civilization. We are slowly building the ability to survive cosmic threats. But for now, we are all on this tiny rock, spinning around an ordinary star, in a quiet neighborhood, hoping the universe is gentle with us, hoping that death beam misses us. The stars are not our enemies. They are our ancestors. They created the elements in our bodies. They made life possible. They are beautiful and dangerous, just like the universe itself. We are a delicate oasis in a universe that is indifferent to our existence, a universe of exploding stars, of neutron star collisions, of death beams aimed across the cosmos. But we are here. We exist, and we have the ability to understand the universe, to see these events from billions of light years away, to trace our origins to the death of a star. The universe is watching. Are we paying attention? So the next time you look up at the night sky, remember, some of those stars are dead. They just don't know it yet. And the light you're seeing, it traveled across the universe to reach your eyes. It was created in nuclear fusion, forged in the heart of a dying star, and it arrived here, on Earth, where life exists against all odds. We are the universe experiencing itself. We are the result of 4.5 billion years of evolution. We are the guardians of this tiny blue dot. And as long as we exist, we are the universe's only way to understand its own beauty, its violence, its majesty, its fragility. The universe is watching. Are we paying attention? Let's imagine a scenario. A GRB hits Earth. The ozone layer is destroyed. The UV radiation kills the plants. The oceans die. What happens to the survivors? The survivors would retreat underground, into bunkers, into caves, into any place that shields them from the UV radiation. They would live in darkness, protecting themselves from a sun that has become a killer. Food would be stored, water would be filtered, medical supplies would be carefully rationed. The survivors would be fighting a slow battle against time, waiting for the ozone layer to recover, waiting for the UV radiation to fade. A child is born underground, the first generation born after the GRB. They have never seen the sun. They have never felt the wind on their face. They have only known the bunker, the darkness, the fear. Will they ever see the stars again? Will they ever feel the warmth of the sun? Or will they spend their entire lives underground, waiting for a recovery that might take centuries? Decades later, a scientist steps out of the bunker, wearing protective gear, measuring radiation levels. The UV radiation is still deadly, but it's decreasing, slowly. The ozone layer is recovering. The sky is clearing. The brown haze is fading. A faint blue appears. The sun is still dangerous, but it's no longer a killer. There is hope. A seed is planted in the soil, the first plant after the GRB. It grows slowly, reaching for the sun. It's a symbol of recovery, of hope, of life finding a way. The child, now an adult, steps out of the bunker for the first time. They see the sky. They see the sun. They feel the warmth on their face. They cry. They survived. Humanity survived. The earth recovers. Slowly, over centuries, life returns. The forests grow back. The oceans teem with life again. Human civilization is smaller, more fragile, but alive. A reminder that life is resilient, that hope endures. We live in a universe that is beautiful and indifferent, full of wonder and danger, a universe that gave us life and could take it away in an instant. But that's what makes life so precious, the fact that it exists at all, against all odds, on this tiny planet, orbiting an ordinary star in a galaxy of 100 billion stars. We are connected, all of us, by our curiosity, by our awe, by our desire to understand the universe, to understand ourselves, to understand what it means to be alive. So look up at the stars tonight, and remember, you are made of stardust. You are made of GRB debris. You are the universe's way of experiencing itself. And right now, in this moment, you are alive, against all odds, on this fragile oasis, in a universe that is beautiful and indifferent. So live, breathe, and wonder.